So, hi guys, I am Navpreet Singh from McGill University here in Montreal. So, our research group is currently working on different kind of sensors, including GaN sensors, and I am here to present a paper on realizing a highly compact particulate matter sensor with a MEMS-based resonant membrane. Now, when I discuss my research with other people, I have realized that not many people have an idea what particulate matter is. So, I'm going to start with that. What is particulate matter? And then we're going to study the classification of PM, what are the different existing technologies to measure PM, and then I'm going to present our proposed solution, our tests and experiments, and then we are going to conclude. So what is particulate matter? So particulate matter is a complex mixture of extremely small particles and liquid droplets. These are present in the ambient air. They can be nitric and sulfuric acids, they can be organic chemicals, they can be metallic fumes, and also soil and dust particles. Now these can originate from the source in the form of particles. These are called primary source. These can be construction sites or unpaved roads from smokestacks. And also they can come from sources which are termed as secondary because they are a result of a chemical or a physical process. These can be industries, some power plants or automotives. Now based on their aerodynamic size, these particles can be categorized into three different categories. The first one is PM10. So these are the particles that have aerodynamic size less than 10 microns. Now these particles can reach your throat and can cause irritations. And the second category is PM2.5. They have their aerodynamic diameter less than 2.5 microns. They can reach your bronchus and they can cause acute diseases. And the last category is the ultrafine particles. These are the extremely small particles and the most harmful ones. They have aerodynamic diameter less than 0.1 micron. They can penetrate deep into your skin. They can also enter your bloodstream. They can reach the deeper parts of your lungs and can cause chronic diseases. In this diagram down here, we have a size comparison of a human hair with PM2.5 and PM10. So human hair is mostly 50 to 70 microns in diameter. So compared to this, PM10 and PM2.5 are almost invisible to naked eye. Now we know what is particulate matter, but why do we need to measure it? World Health Organization reports that every year there are around 7 million deaths in the world that can be attributed to this particulate matter, both indoor and outdoor. If countries can reduce air pollution, they can reduce the risk of stroke, heart diseases, lung cancer, and other diseases including asthma. As such, World Health Organization has set a limit on how much of this particulate matter can be inhaled without causing any serious risk to the health. So World Health Organization has guidelines on the annual mean and the daily mean for both PM2.5 and the coarser particulate matter, which is PM10. Now here we have a bar graph. So the x-axis, the yearly PM2.5 concentration, and the y-axis states some world capitals. And this blue line here is the World Health guideline of 10 microgram per meter cube. So we can see countries like Canada and Sweden, they have very clean air, but the people in countries like India or Dhaka and Kabul, they are not very fortunate because air quality is 10 times worse than the prescribed limit by the World Health Organization. Now there are two existing technologies which can measure PM. They are classified as gravimetric and optical. Now gravimetric methods, in this you directly measure the mass of the particles. So what you do is you collect particles over a tape and then you take that tape to the lab and measure the amount of particles. You can do this for like every hour, daily, or over a week. But there are a few shortcomings to this method. These methods are very pricey. They run you into thousands of dollars and they're bulky in size. They don't provide real-time data because you have to collect the particles, take it to the lab, and then you know how much particulate matter is there. So they're not suitable for personal health monitoring because of the size and the price. And the second method are optical methods. Here, you don't measure the mass of the particles. You measure the number of particles. So what you do is you use a laser of a certain wavelength, and when you shine the light on these particles, then you measure the amount of scattering from these particles. That can give you an idea of how much particles are there in the chamber. But there are a few shortcomings. These are still pricey for low and middle income countries. And as I told you, they can measure just the number, not the mass. So they have to assume a certain density, certain size distribution. This can result into inaccurate results. And also optical elements are sometimes sophisticated and are complex to use. So we need a better solution, a solution that is affordable even in low and middle income countries, a solution that is portable, should be small enough so that it's good for personal health monitoring, and system which is easy to use. You can use it as a standalone device, you can put it in a smartphone, you can put it in a smartwatch. So here we are trying to propose a solution that tries to meet all these three requirements. Our solution consists of three mechanisms. First mechanism is to segregate the particles based on their size. As I told you, there are three different categories. So you you segregate them according to what you want to measure, whether you want to measure 2.5, 10, or ultrafine particles. And second mechanism is one for sensing the particles, which is currently the focus of our paper. And the third mechanism is to reset the sensors. Now you have segregated the particles, you have measured them. Now you want to reset the sensor because you want to take another measurement. So for the first part, to segregate the particles, we are going to use microfluidic channels, which are termed as virtual impactor. So when you have a fixed flow rate at the inlet or the outlet, you have this kind of velocity profile created in these channels. And when you have your particles incoming from an inlet, so this is the device that we have simulated in COMSOL. So here we have a fan to maintain the flow at the exit. So when you inlet your particles from the entry, the heavier particles, let's say PM10, they are heavy and they have higher inertia. They will tend to follow a straight path in this straight line. But the lighter particles, say if you want to measure PM 2.5, so you design it accordingly, and those particles will segregate into a separate chamber, where you can place your second mechanism, which is a sensing unit. And I will describe this in detail. But the third part, which is to reset the sensor, for that we are using two plates called thermophoretic plates. So what you do is you have a hot plate, you have a cold plate, and you maintain a temperature gradient between them. So the hot air molecules from the hot plate, they will try to go towards the cold plate, and while doing so, they will collide with the particulate matter, and it can force them down towards the cold plate. And you can put your sensing device here, and you can take the measurements. And when you want to reset it, just make the temperature opposite, and it will repel away the particles. We are also thinking of making a slight modification, using a resonator as the cold plate, and just doing this with just one plate. Now for sensing mechanism, the choice of resonators that we have selected is piezoelectric resonators. Now why? Because they have high electromechanical coupling, so they have low impedance levels, they have low geometrical constraints, it's easier to release the membrane of a piezoelectric device, and also they need low biasing voltage. So the interfacing electronics will become simple. Now this is the equation called Sorbray's equation that defines this mass loading effect. So it states that with every delta M mass deposited on this membrane, you will see a negative shift of delta F in the resonance frequency. And this delta F shift is proportional to the frequency of the membrane, its geometrical parameters in terms of the area of the membrane, and its material parameters in terms of membrane's effective density and its shear modulus. So we are going to use this as a sensing mechanism. So when particles will deposit on this membrane, there will be a shift. We'll read this shift and try to judge how much particles are there. Now to fabricate our devices, we used a commercial multi-user MEMS process from a company called MEMSCAP. It's sponsored by CMC. So we start with the silicon on insulator wafer. And in the first layer, we deposit pad oxide. So pad oxide can be used to isolate your signal from the ground. And the next is the piezoelectric layer. So in our case, it was aluminum nitride, and it was 0.5 micron in thickness. And then you deposit the pad metal. So as I told, this pad oxide here is used to isolate this signal from the ground. So, and this is the ground. And the last step is you can etch the trench below it. Now you have released your membrane. So now you have your hanging membrane, you have your anchors on the side, and this is your resonator that we can use. So we got this device fabricated, and this is the SEM image of the resonator. So here you can see the silicon membrane and the piezoelectric layer and the aluminum electrode on the top. It's connected to the signal pad here, and the ground is connected to the silicon. And this is the side image. So you can see this is the 10 micron thick silicon membrane, which will work as a resonator. And this is the 0.5 thickness aluminum nitride, which is the piezoelectric material in our case. So we used COMSOL multiphysics to simulate our devices. So what we ran a parametric sweep. so that we can find the optimum length and width of these anchors that can provide us a high quality factor for these resonators. So what we did in the simulations, we kept depositing a mass in quantity of 0.01 micrograms. So whenever we deposited 0.01 microgram on the membrane, there was a negative shift in the resonant frequency, as you can see in this plot. And this shift was supposed to be linear as defined by the Sorber's equation. This console simulations for this particular dimensions gave us a resonance frequency of 1.102 megahertz. And we simulated a device to have a sensitivity of 1.226 kilohertz for deposition of every 0.01 micrograms. Now, when our devices were fabricated, we characterized the devices using vibrometer and VNA. They both agreed in a result and gave us a resonant frequency of 1.0225 megahertz. This is a bit off from the simulated values. We think this is because of the residual stress in the membrane, also because of the process variations. And to test these devices, we took our dies with the devices. We bonded them to LCC 28-pin package. And then to emulate the particle source, we used an incense stick. Now, incense sticks are usually burned during religious festivals in Southeast Asia or in Middle East. So these are known to emit smoke which contains particles of various different diameters, and it also consists particles which are around 2.5 micron, which we were targeting. And we used this incense stick and we kept this everything in a container. So this container was 51 liter in volume, carefully sealed from all the sides. We carefully sealed these outlet ports. We used a custom PCB to place our dies inside. And when we burned this incense stick, the smoke was generated and was trapped inside the container. So that led to the accumulation of particles in the chamber. So eventually these particles are going to settle down on the floor of the chamber and also on this chip. And we can detect the shift in the frequency using a VNA. So when we used VNA, we got the shift in the transmission curve. So we ran our experiment for 35 minutes and we took measurements after every 5 minutes. And we saw that with continuous deposition of the material or the particles on the membrane, there was a shift in the resonance frequency. We translated this curve into frequency versus time domain. So you can see we have taken measurements at every 5-minute steps. So there is small anomaly. So this small step in the beginning is because at this time the particles were just starting originating from the incense stick. And there is this sharp decline in the frequency at about 25 minutes. This was because at this time the incense stick was fully burnt and there was no more accumulation of particles that disturbed the settling. So using this, we have established that piezoelectrically actuated resonating membranes can be used for detecting the particulate matter. So now after submitting this paper, we started working on the other part, which was to segregate the material. We have got the devices fabricated. We have in fact got 2 devices fabricated using CNC machine milling and by 3D printing using transparent resin. And we are in the testing phase. So once we have done all this and plugged in everything together, we are thinking of providing an affordable particulate matter sensor, because we are going to use MEMS technologies. It brings down the cost when you produce in high volume. We are going to bring portability, because the final design is intended to be 2 centimeter by 2 centimeter by 1 centimeter, which is one of the smallest realizations of this sensor, this kind of sensors. And also it's so small you can put it in your smart devices, you can put it in your air conditioners, you can put it in the humidifiers. And these are going to be easy to use. You don't need to go to lab to measure what the amount of particles have been collected on this. And it's going to give us high performance because it's supposed to have high sensitivity. It's going to give accurate results coupled with real-time sensing. So this is our work. This is now the initial phase and we are working on the second part. So yeah, thank you. Thank you so much. And we would like to thank these institutions for helping us realizing this idea. Thank you so much.